I can cancel out this one as well, but this one make it 4, and this one becomes 4 as well. We have d cubed and d squared, so let's just like cancel like 2 of this and the same thing here. Okay. And I can take 4 out. So like it simplifies into this one. Delta IL squared divided by 4. Okay. Actually, I can take 3 out too. 3 multiplied by 4. Multiplied by, here we have only one d, and here we have 1 minus d. Okay. Which it's going to cancel out, it becomes 1. So the whole thing becomes square root of delta IL squared. I can take it out of the integral. 4, I can take it out of the integral 2, and this becomes square root of 3. Okay, so in your lecture notes, when you see this waveform, here is delta IL divided by 2, delta IL divided by 2, and the RMS value is shown as this. You can actually do the calculation, find it out. I don't expect you to do this in the exam or in the assignments, but you can just like, now you know like how this is derived. Okay, so now we know the concept of DC and RMS values of periodic functions. Okay, let's do a quick review of maybe I'll do a quick review of buck converter first. This part is very important because the rest of the calculation all depends on the values that we're going to find out here. So I hope you can see the whole thing. Let me make sure that everything is clear. Maybe move this a little bit further. Okay, so this is the buck converter. Right, so this is the switch. Can be a MOSFET or IGBT. This is a diode. This is, let's say this is VL. This is VR, sorry. This is VC. This is IR. And this is IC. This is IL. This is I switch. Let me write this down with IQ. And this one is I diode, and this one is V diode, and this one is V switch, VQ. Okay, so we're gonna find the waveforms of all of these variables and find the RMS values of, and RMS and average values of them. So this calculation is done in the steady state, in the CCM mode, right? And we also have this assumption that this capacitor is big enough so that output voltage doesn't change much. So also we can assume that the output current is constant. Okay, so we basically assume that V in, V out, I out, these are constant values. Okay, same as RLC. Okay. But V in and IO can change with the duty cycle of the switch. So these are the assumptions we have. This is our input voltage. Okay, and this is the I in. Okay, so first of all, let's look at our input voltage. Vi of t over t. This is always a constant. Okay. Now let me look at the, as we did in the class, let me take a look at the inductor's voltage, the voltage across the inductor. Okay, so for the duty cycle D, this switch is on, right? So when the switch is on, the voltage across the inductor, it's going to be V in minus V out, right? So like when this is closed, this is going to be V in minus V out. So for the first dt seconds, this voltage is Vi minus Vo, right? And once this switch is open, right, our inductor voltage, you can see that the diode it's going to conduct, our inductor voltage is basically the same as our output voltage, but in the reverse polarity. VL becomes equal to negative VO. So this is what's going to happen. Okay. And you guys remember that based on volt-second balance, this area has to be equal to this area in order to stay in the steady state. Okay, if we have this, now it's easy to draw the inductor current, IL of t over t. Assuming that we have an initial current here, the inductor current, it's gonna be for the first dt second, it's going to increase with the slope of 1 over L times Vi minus Vo. And for the next part, it's going to decrease to the same level with the slope of a negative 1 over L divided by Vo. Okay. Here some people like put average here. This is like basically average, but like we assume that VO is constant. Okay. Now let's take a look at this diode. So I want to know like what's the voltage across the diode. When this switch is closed, right, the voltage at this node would be equal to V in, and this point is grounded, right? So the voltage across the diode from anode to cathode, it's going to be negative V in, right? Because this point is 0, this point is V in, so this is going to be negative V in. Oops, sorry. And when the switch is open, the diode is conducting. So like the voltage across it is basically 0. Okay. Let's take a look at its current, the current that goes through the diode. I of diode. Okay. So for the first dt seconds, how much current goes through the diode? The diode is open, right? It's reverse bias, so the current is equal to 0 for the first dt second. And after that, when the diode is conducting, its current is basically the same as the inductor current, because then